Yes, thanks for the introduction and for the invitation. I would have really loved to join the hike and also discuss, like, be there in person and discuss with everyone. But we actually just bought a house in the beautiful forest outside of Stockholm, and we moved in just a few days ago. And we also have a 6-month-old baby, so it's just super chaotic right now, and I felt a little much.
Do you have a possibility of using a microphone, or are you using one?
I thought I'm using those, but I don't know if I can somehow change so you don't hear me well.
I hear you, but it's a bit distorted.
Okay.
Quality
I don't really know what to do because I assume that it uses my headphones because I hear you over those at least.
Okay.
I can just try to talk very clearly, if that's okay. Right. So in any case, I want to present some joint work with Matthew Trager and Guido Montúfar and Guido's student Thomas Merkh. And so we are studied linear convolutional networks. Just for our main motivation was to see how linear dense networks compare to linear convolutional networks, to try to get some sort of theoretical understanding what, like, if you introduce convolution to a network, what happens to, for instance, questions like expressivity and several optimization questions. But in principle, you hear what I say.
Yes.
Yes. Is that okay? Okay. So if there's a question, I'm, as in the other talks, just interrupt anytime. I'm very happy that you that's how it works in this workshop. So let me tell you first, to fix notation, what I mean with a linear convolutional network. On this slide and for most of the talk, I will focus on one-dimensional convolutions. And so, as we all know, a network is just a family of functions. In my case, this is a linear function, since I'm doing theoretical study of linear networks. And so this linear map is represented by a matrix W. And so W factors into L matrices for the L layers. And the fact that I'm dealing with convolutions means that these layer matrices are not arbitrary, but that they are convolutional matrices. Okay, somehow something is missing actually on these slides. I don't know why exactly. 1 second. Maybe I have to do this so that you cannot see me, but I guess that's okay. Somehow it doesn't show the things that I pre-wrote on the screen. So I will just do this again. Right. So a convolutional matrix has the property that each row is just a copy of the previous row, but it's shifted by some strides. And so the strides, I write here small s. That's the stride size. And in each row, you typically have, in the first row, you have just the first entries being non-zero. And that's called the filter. So that non-zero vector, that's part of the first row, is the filter. And so the filter sizes, I write small k. So there's lots of parameters here, but I try to keep it very simple. And then you have a certain number of rows, which is then determined by the number of rows, small di, of such a matrix. So the important parameters here are somehow the number of rows of each matrix, the number k, which was the size of the filters, and the strides. And so here's like a very explicit example of how such a convolutional matrix looks. Okay. And so these, if I have now many layers, then the tuples of all of these numbers for all the matrices, they are somehow determining the whole architecture of a linear convolutional network, which I will write LCN for abbreviation. Okay, so that's the notational setup. And so what I want to do, I want to talk about this expressivity question. So what can we say about the function space about such networks? And then I want to talk a little bit about optimization questions and give a short comparison to dense networks that are linear. So the function space of a neural network in general is just the set of all functions it parameterizes. So in our case, this is some sort of set of matrices, and all these matrices, they have to be factorizable into these convolutional matrices. I wrote it just shorter here, with the correct strides and filter sizes, right? And so the question is, how do these strides and filter sizes change the architecture, change the geometry of this function space? Because the shape of this function space is, of course, very important for the behavior when you do optimization. So the first very easy observation you do in linear algebra 1 is that if you have a convolutional matrix or many convolutional matrices and you take their product, you will get again the convolutional matrix of a certain filter size, and here's the formula, and of a certain strides, which is just the product of the strides. So that's an easier formula. And so that is in some sense nice, because there is here this corollary that I wrote, which looks a little bit technical, but what it says is that this function space of the network architecture is actually contained in some natural ambient vector space. Yeah, so this is just a set of all convolutional matrices with filter size k and stride s according to this observation. Yeah, so that makes sense. I want to somehow see our function space might be a very complicated set, but it sits inside some very natural vector space, and vector spaces, we understand they are easy in some sense. And one natural question that comes to mind immediately is, well, if the function space is contained in this beautiful vector space, is it actually sometimes equal to the whole vector space? And that's an interesting question, because if your function space is itself a vector space, then doing gradient descent or solving other convex optimization problems is actually mathematically a very tractable problem. Yeah? So that's why it's interesting to understand those architectures where this function space actually is equal to the whole ambient vector space, and we call those filling. Is that setup clear so far? So I will first try to answer this question when this equality happens. Okay. And yeah, it's easier to do this for stride 1. So let us do this very in detail, and then I will say what happens when we go to other strides. So a stride 1 convolutional matrix now has just every row is shifted by 1 from the previous one. And it's very natural also in signal processing to identify such convolutional matrices with polynomials. So I have this nice projection where you just take the entries of each filter as the coefficients of a polynomial. So I have k entries in each filter, so I get a polynomial of degree k-1. And mathematically, it's just easier to work with homogeneous polynomials. So that's why I am now introducing 2 variables, x and y, to be able to have homogeneous polynomials instead of univariate polynomials, okay? And under this bijection, what is nice is that the product of convolutional matrices is just corresponding to the product of the polynomials. And I'm an algebraic geometer, so I like a lot of products of polynomials. Okay. So now we can really use this polynomial world to understand the function space in very, very much detail. So that's, I think, is very nice. So this theorem says that a matrix can be parameterized, that you can obtain it from the linear convolutional network with a fixed architecture, if and only if the corresponding polynomial has at least a certain number of real roots. And this number E, that I call it here, is very easy to determine. It's the number of even filter sizes in your architecture. So the only thing you have to do is to look at the two tuple of filter sizes and count how many even numbers you have there. And the set of all polynomials with that many real roots or more is our function space. In particular, these sets are kind of well studied throughout the history of mathematics. I want to say at least the recent hundreds of years. And so this set of functions is a full dimensional subset of this beautiful ambient vector space that I hope you remember. And it's in fact a nice set. It's in the sense that it's semi-algebraic. So the set itself can be described the way it sits inside the ambient vector space by polynomial equalities and inequalities. Okay. Is there a question so far? Do you still hear me okay?
I wonder whether you can switch on again your video. Or is it really
if I can show what?
Whether you can switch on your video again.
I don't think so. Somehow, I mean, I think I would take like a few minutes because if I would do that, yeah, somehow on the iPad it happens when I leave Zoom and go to a different application, it just automatically turns off my video. And now I try to share the slides directly via Zoom, but then it doesn't show the things that I wrote on the slide by hand. That's worse. I rather want you to read what I wrote than to see me, unfortunately. Okay. Otherwise, I would have to now try some other application, and I think that's maybe not so good at the moment. But you will see me at the end. Right. The last part of this theorem is that I can tell you when this architecture is filling. So remember, this means that the function space is equal to the nice, beautiful ambient vector space. And that happens if and only if this magical number E is at most 1. And so I am not a machine learner at all, but people have told me that actually in practice, convolutional architectures, they're of course not linear, but they often use filter sizes that are only or consisting of even numbers because apparently experimentally they behave well. So now, for linear networks that are not used in practice, there is a reason, because if you have all filter sizes should be odd, sorry. Because if you have all odd filter sizes, your architecture is filling. So your function space is a nice vector space, in fact. And you're allowed to have one even filter size in between the things. So let me tell you a concrete example. What happens when this magical number E of even filter sizes is not 1 or 0? So the first interesting case is when I have 2 even filter sizes, right? So now my function space is the set of all polynomials. If you think about it, these polynomials now need to have even degrees. And so this is all polynomials with at least 2 real roots. That was the theorem on the previous slide, right? The function space is those polynomials with at least E real roots, and E is 2 in this example. Okay, so the complement of the function space, since I'm dealing with polynomials of even degree, is now those polynomials that have no real roots at all. That's a very well-studied set. It's the union of 2 convex cones, namely the positive polynomials and the negative polynomials. So a polynomial is called positive when it evaluates to a positive number everywhere. and vice versa. And so here's like a nice picture, how you can think of it. So the interior of the cones is the complement. Yeah? So the function space is everything that's not inside of those cones. So this is how this function space looks in this example. So for two even filter sizes, this is very explicit. For larger amount of even filter sizes, it gets a little more difficult, but since now the function space is not equal to the whole ambient vector space, but it's a full dimensional set in there, it's some full dimensional set, it would be interesting and important to understand the Euclidean boundary of that space, right? Because the Euclidean boundary will be often, when you do optimization, you will find the critical points typically on that boundary. So it would be good to have a better understanding of this space. So let me tell you how this boundary looks in the case where we're dealing with stride 1 convolutional networks. This is also very explicit, but I need yet another notation. I guess you have seen this before in one way or another. There's not really a standard name for this, but we call this a real root multiplicity pattern, RRMP, of a polynomial. And what this is you take your polynomial, then you factor it into its irreducible factors over the real numbers. Right? So I have a real polynomial, and you think about your algebra class, it's going to factor in a bunch of linear terms and quadratic terms. And then I'm just recording the multiplicities of the linear factors. This is my numbers row, the row 1 through row R. These are just the multiplicities of the linear factors, so the real roots. And then I also record the multiplicities of the quadratic terms. So each quadratic term corresponds to a pair of complex conjugate roots. Does that make sense? So I'm just taking a polynomial, I do its irreducible factorization, and I record the multiplicities I get in the exponents. And that's what we call the real root multiplicity pattern. Now I want to make a first exercise, namely I'm restating the first part of the theorem from the previous slides. Namely, in this notation of a real root multiplicity pattern, a matrix is in the function space if and only if its corresponding polynomial, as I said, has at least e real roots. And the fact that it has at least e real roots just means that the sum of these row i's is at least e. Okay, that was a warm-up exercise to get used to this new notation. Actually, I also could have said this earlier, but it's easy to see in this setup that also this function space, as I said, it's a full dimensional subset inside the vector space. It's semi-algebraic and it's closed. So it's in some sense as nice as it can be. So the boundary of the space is also part of the function space. And now I can tell you exactly how points in the boundary look. Namely, this is all polynomials that were first, since it's closed in Euclidean topology, they have to be in the space. So the number of real roots should be at least e. And then you have another funny exercise here. You count how many of these row i's are now odd. And this number has to be at most e minus 2. So it's a very specific thing. I will do an example on the next slide. And for an algebraic geometer, it's interesting just to note that the Zariski closure of this Euclidean boundary is in fact just the discriminant hypersurface. So the polynomials with the double roots. So that's a very well understood hypersurface. But the actual Euclidean boundary is a more complicated part of this hypersurface. Okay, so let's do an example. Let's try to memorize this point 3 of the theorem. Matrix is in the boundary if the corresponding polynomial has at least e real roots, and you count how many of its row i's are odd, and that's supposed to be at most e minus 2. Okay, so now the example. So here I'm dealing with a network with 3 layers that all have stride 1, and all filter sizes are 2. So I have 3 even filter sizes. So my magical number e is equal to 3. Now in the first line of the slide, you see the 3 convolutional matrices that are going to be, I'm taking the product of. And below those, you see the corresponding polynomials. Yeah, so each layer matrix corresponds to a linear polynomial, and their product is going to be a cubic polynomial. And so the whole question is now, which cubic polynomials lie in the function space and which of those actually lie on the boundary? Now we can make this very explicit because a cubic polynomial, very well studied throughout the recent, as I said, hundreds of years, has just 4 different real root multiplicity patterns. So this table in the bottom left, you can read as follows. The first entry, 1, 1, 1, 0, just means that you have 3 real roots. And the next entry means you have 1, 2, 0. That means that you have 1 real root, a double real root, and still no complex roots. The next line of the table means I have a triple real root. And finally, the last line of this short table means you have 1 real root and then 1 pair of complex conjugate roots. And so, according to the theorem from the previous slide, my magical number e is 3. So I need to have at least, what did I say, at least 3 real roots counted with multiplicity. So the first 3 lines of the table, they correspond to the function space. And to be part of the boundary, I also need this other condition that I repeated there in my yellow handwriting on the top right of the slide, namely that the number of odd row i's has to be at most 1 in this example. And you can just look at this table and then you see, oh, you know, I have marked those 2 rows in yellow where this works. So it's very explicit in for concrete network architectures. And then I try to make like a picture here of the function space, which I'm not really sure how elusive it is, but yeah, that's how the discriminant hypersurface looks for cubic polynomials. Does that make sense, the question or something?
Oh, good.
Good, then I have another concrete example. I'm still with stride 1. And now I'm bringing this example because sometimes different architectures can have the same function space with the same Euclidean boundary. And so this is one of the smallest, but yet interesting examples there are. So on the right, we have the architecture 4, 2. So this means I have filter sizes 4 and 2, just 2 layers. And that corresponds to multiplying a cubic polynomial with a linear one. And on the left, I have 3 layers corresponding to a quadratic polynomial and 2 linear factors. And so the function space is equal because the function space is only determined by how many of my filter sizes are even. And in both of these examples, I have even filter size. Okay, so we can also, you know, we're dealing now with quartic polynomials in total, and so now it's slightly more complicated. You could do the same exercise, write down all the possible multiplicity patterns, and then you just use the theorem, very easy, you know, by counting, you know, the row i's and so on, and to figure out how the Euclidean boundary looks of the space. Okay. What do I want to do next? Now we can really understand super well the architecture for stride 1. We can understand at least how the function space looks and its Euclidean boundary where we know that the critical points would typically be if I do gradient descent. So what happens for larger strides? That's actually some work we're doing at the moment with one of my PhD students. But what I can tell you at the moment is it's getting more complicated. You can still identify convolutional matrices with larger strides with polynomials, but now you will have to use somehow a different identification, as you see here in the first line of the slide. I am not just recording somehow a standard polynomial, but I'm using x to the power of s and y to the power of s somehow as my ground variables, and then it gets more complicated. You cannot just say anymore that the product of convolutional matrices immediately corresponds to the product of polynomials, because this, where you see why I underlined it in yellow, it's a little bit funny that if you just take the product of two convolutional matrices, it does correspond to a product of polynomials, but for the left matrix, you have to use the stride of the right matrix. And for the right matrix, you just use stride 1. So if you do this for larger amounts of layers, it works like this inductively, of course, but it gets more messy. And I am not telling you the details of the slide, but essentially what changes drastically is that the function space is now always going to be a low dimensional set in the natural ambient vector space. So previously, as I told you, where we had stride 1, our function space was a full dimensional subset of the vector space, and I could understand its Euclidean boundary very easy, and it's a nice picture. But now the function space is becoming a very small low dimensional set, and that makes also the optimization behavior quite different. So here is like a formal theorem that has some conditions, but the conditions essentially say, if your network is not secretly a stride 1 network or a trivial network with just one layer or something, then you're always going to be lower dimensional. Okay. Also, for higher dimensional convolutions, you can do a similar story. Now you have to deal with tensors. I'm not going to do the details now, but I can also send you the slides later. Who is interested in the details can read that outside of this talk or ask me later. So now we just have to deal with tensors instead of matrices. You can still get a nice identification. Now you need to have polynomials in many more variables that are homogeneous in pairs. But then, if you take the correct product of tensors, it corresponds to polynomial multiplication, so that's nice. And the end of the story is a similar one to the previous slide, that the function space is going to be a low dimensional set of the ambient vector space, unless your network was secretly actually a trivial one. So that's just what this theorem says. Okay. So that was somehow what I wanted to say about the function space, about the expressivity, about these networks at the moment, and about their Euclidean boundary. So now would be also a good time for questions before I say something about the optimization.
Yeah, maybe I have a question. Is there any perspective to extend this beyond linear networks?
Good question. So this is always the very difficult part, right? So I mean, one thing we want to do is definitely look at the value networks, because we do think that some of our techniques could be used into two directions. Either one could attempt to do value networks on the one hand, and on the other hand, maybe less interesting for practical purposes, is you could look at the polynomial activation functions, right? Again, maybe value networks is more interesting for practice, so Yeah, we're not doing this at the moment since I'm still not really back working full time, but we want to do this once we have a better understanding of larger strides, for instance, in this linear setting. Yeah. So that's a good thing to do, I think.
Okay, thanks.
Right. So now I want to study the problem of optimizing a loss function. And since at the moment, our best understanding is for one-dimensional convolutions with stride 1, I want to somehow paint a complete picture by understanding the optimization behavior in that setting. So that's what the rest of the talk will focus on. So let's recall that a loss function on a neural network in general is a function that decomposes typically in two parts. Here, the function mu is just the parametrization function that you get from taking the products of the layers. And small l is the actual function you're imposing. You know, it could be the Euclidean distance or Wasserstein distance or something. I'm assuming here at the moment that the small l is smooth. And if we are doing gradient descent, then we're doing gradient descent in parameter space. And it's interesting to understand critical points there. But from a mathematical perspective, it's typically easier to analyze the critical points in the function space that we just described. And so the question is, how are those related, right? And so this is generally true, and I think you all know this, of course, also very well. You know that if you have a point that's critical in function space, then every set of parameters that parameterizes that point is also a critical point in parameter space. That is just chain rule. Yeah. So the interesting question is always, what can I say the other way around? So if I now have a critical point in parameter space, what's up with the product of the matrices in my case? Sometimes that's what we want, that this product matrix W also actually is a true critical point, preferably a very good local minimum or something like this in function space. But sometimes they are not. Yeah. So sometimes critical points in parameter space do not give me critical points in function space at all. And so these are in some sense spurious critical points that I purely have introduced by the way I parameterize this set of functions. Okay, so that's an interesting question to study, which I want to do. Right. And to answer this question, we first did some sort of numerical experiments. We also have some nice theorem explaining those actually later, but I want to motivate my theorems by first also looking at our experiments and being a little bit puzzled by that. So here is an experiment where I'm dealing with a network architecture that has two layers. We have seen this before in one example. What I'm doing here is I'm taking the product of a cubic polynomial with a linear polynomial to obtain a polynomial of degree 4. And now what do we see in this table? So on the left column that I labeled target means that I have some sort of target polynomial that I want to reach via gradient descent. I'm using the square laws as the optimization function here. And what we did is we initialized our network in some random way. And then these are, in this case, always polynomials that have all 4 real roots. So now my point is that I'm initializing my network at some sort of random point in the interior of the function space, but my target polynomial, we also chose this randomly, I forgot now how, some Gaussian distribution, I guess, it's a long time ago. The target polynomial is sometimes inside of the function space and sometimes outside of it. And then we ran gradient descent, And then we just recorded where we stopped, at what sort of critical point. So if you just look at the first row of the table, we see that if I start from a point inside the function space, and I also want to reach a point inside the function space of the same sort of real root multiplicity pattern, we always actually found the target point. So that was nice. Now in the second row of this table, you see I am starting inside the function space. I want to go to another point inside the function space, but it's a different one. Like geometrically, it's a different point because now this polynomial has a different real root multiplicity pattern. And we often found that point, you see 83%, but not always. Like sometimes we didn't find that point. We found a different point, either in the interior or even on the boundary of the space where we got stuck. And most interesting for me is the third row of this table, because now I'm starting from a point inside the function space, but I want to go to a point outside of the function space. And I am expecting to land on the boundary, right? So if I try to draw yet another picture here on the slide, so this is my function space. I start from a point here. I want to go to a point outside. So we're somehow expecting that I should hit the boundary somewhere there. But in some non-negligible amount of cases, maybe about 8% of the cases, it didn't happen. We stopped somewhere here. We got stopped inside of the function space. We never actually reached the boundary as we should have. And these are points that are the spurious critical points that I meant. So we are going to find those. We are going to find critical points that are purely introduced by how we parameterize the function space, and they are bad critical points. And we don't want to find those in practice, but we are going to find them. Okay. And there is yet another table, which I'm not going to explain in so much detail, but I want to remind you of this example I had earlier, that I compared these two architectures. Now the left one has 2 layers, the right one has 3 layers, but they have the same function space, yet the optimization behavior is very different. And if you have time, you can study this table and be puzzled a little bit by it. And so somehow what's interesting is we're dealing with quartic polynomials in both cases, but somehow which types of polynomials appear as critical points is very, very different. Although we're dealing with the same function space. And somehow this suggests, that deeper architectures, although they might give the same function space as a more shallow one, but the optimization behavior can be quite more complicated. So now I want to spend the last minutes on explaining somehow the theorem that actually says that these two tables should exactly look like this, like that this was expected. Okay. So to do this, the last piece of notation I want to define is for your favorite real root multiplicity pattern. I'm now going to define this delta locus. So this delta set is just all polynomials, if you want, that have that real root multiplicity pattern. Yeah? So you pick your favorite one, your favorite row and gamma, and then delta is just a set of all polynomials with that real root multiplicity pattern. So now I am wanting to understand this critical point question. So I have a matrix W that is the product of a bunch of layer matrices, convolutional layer matrices, WL through W1. And I assume that W has this fixed real root multiplicity pattern, rho gamma. So now what I can say first is that if these parameters as a critical point of the network, then the product matrix W is a critical point of the loss function, but not necessarily in the function space, but always on this delta locus, which is a different set. That's always going to be true. And this I can also make a vice versa here. So if I have that W is such a critical point on its delta locus, and none of its factors has a double root, then the parameters are a critical point of the network. All this looks a little bit technical, but bear with me. The second point is actually typically an if and only if. So what we managed to prove formally is that if I'm dealing with the square laws and I have somehow random enough training data, then the second part of the theorem is an equality. And this gives me yet a different way to understand all critical points of the network. Because I just tell you in part 2 of the theorem that all critical points of the network come in such a way that the function space matrices are critical points on the delta locus such that the products do not have a double root. And these things are, well, in some sense, easy to check. So this actually gives an algorithm to, in advance, before even running gradient descent. But what I can do now, if you tell me point, I can just compute all possible critical points using this theorem in advance. Okay. And so this is nice. And this also is actually a nice combinatorial game that we're playing if we want to write such an algorithm. Because if I have a fixed architecture that I'm studying, and I have a fixed real-root multiplicity pattern, sometimes the polynomials can be factored such that no factor has a double root, and sometimes they cannot. So this is not a property of the polynomial you're looking at, it's just a property of the architecture and of this real-root multiplicity pattern. Let's see, there is an example on the top right of the slides. Okay, so if I have the filter sizes 4 and 2 as in previous examples, and I just, for illustration, I pick a real-root multiplicity pattern where I'm dealing with quartic polynomials with 2 real double roots. That's what the 2 2s mean. And I have no complex roots at all. Okay, so then you see how such a quartic polynomial looks. And your task is the following. You have to take the factors of your polynomial and you have to put them into boxes. One box for the cubic part and one box for the linear part. And you have to do it such that no box has a double root. But that's not possible just by looking at these numbers. So this sort of real-root multiplicity pattern is not compatible with the architecture. And it's a very easy combinatorial game. You have like balls of different sizes that you have to fit into boxes, and either it works or it doesn't. Okay, and so actually this theorem tells you exactly why these tables that I showed you look the way they look. Because so here and on the top of the slide, if I now compare these two architectures, 3, 2, 2, and 4, 2 with each other, I can write down all compatible real-root multiplicity patterns, and you see that the deeper architecture has more of them. I know this is now a little bit technical and it's getting late and people are hungry soon, but somehow to say this theorem in easy terms is that the compatible real-root multiplicity patterns are those that you will find as critical points when you run gradient descent on your network. And you can actually easily implement to find those that are compatible, and you can even use this to compute all critical points in advance, and you can somehow already guess then how these tables look when you run these numerical experiments. So all of this is no magic, and it's very well explainable. Okay, I think I kind of want to maybe stop here. You know, these nice theorems on if you have linear dense networks, there is invariants that have to be satisfied. So when you initialize your points and then you run gradient descent. And so we also have these invariants for linear convolutional networks. And this is what says in this theorem. So you can look at that if you want. And now I just want to somehow end up with this summary of dense networks versus convolutional ones in this linear setting. So the dense networks have been studied very much in the literature. The function space is some nice algebraic variety. It's the set of rank bounded matrices. And now our function space in the convolutional world becomes slightly more complicated, but still very beautiful, because this is a semi-algebraic set. And they correspond to polynomials with certain factorizations. Finally, something that I maybe should have highlighted a little bit more on an extra slide in this talk is that these behave very, very different optimization-wise from the dense ones. Because for dense linear networks, as you see on the left, this yellow equality is very well known and has been observed in many papers. If you deal with a convex loss function, then the network has bad minima if and only if the convex loss function on the function space has bad minima. So non-global local minimum is what I mean with the bad minimum here. And so this is not true anymore for convolutional networks. So even in somehow the nicest settings, you know, you can prove mathematically that if you have a convex loss function, your function space is actually only a vector space, but still your convolutions make it happen such that the networks can have bad minima. Yeah, and finally, you know, the reason is, well, I'm not going to talk about the reason. I should have put this on a different slide, I assume, but it's very different geometric structures that are happening here. Right, and with that, I think I'm done, and I can also stop sharing, and then you can see me. Maybe that's easier with the discussion.